Module 8, Lesson 4 covers scale drawings. For this one, we have got a suggested pacing of 90 minutes, and we have 16 resources to get through, so this may be a one-day, it may be a two-day lesson. When designing a new structure, architects make detailed drawings of rooms, buildings, and even landscape called blueprints. Blueprints are examples of scale drawings. The scale drawing helps the builder determine the placement of elements like electrical outlets, windows, and doors and trees. Yeah, they put trees in blueprints, I guess. How do you think a scale drawing might be useful when preparing to build a large structure such as a house? Well, these are the kind of things we're going to be learning about in this lesson. Scale drawings, also known as scale models, are used to represent objects that are too large or too small to be built at an actual size. For example, if we wanted to take and represent the Eiffel Tower, we couldn't really just put it there. I mean, after all, the Eiffel Tower would be just a little bit large to sit on our desk, wouldn't it? We'd have to have something a little bit smaller, a scale drawing to do it with. So from here, you can see there's a scale drawing of the Eiffel Tower. Here is going to be a model of the Eiffel Tower, and then there's a picture of the Eiffel Tower, which technically the picture is still going to be a scale image because it's not life-size, but hey, that's what the real Eiffel Tower looks like. Our next vocab word is scale. Scale gives you a ratio that compares the measurements of a drawing or model to the measurements of a real-life object. Hanging in my classroom, I've got some old models that I built way back when I was y'all's age, and I always used a 1/48 scale where every 1 inch on the model related to 48 inches on the real plane. Every 1 foot on the model was 48 feet on the real plane. Kind of give you some perspective for how large those really were. Let's see here, the scale here is set at 500 feet per inch in this drawing, so we're going to select some buttons to change the scale to the on-light map and use the scale to estimate the distance between Bowen Road and the intersection off Moorhat Road to the intersection of Blair Road. So we're going to take a look here. We've got Bowman Road here, and we want an intersection between Blair Road and Moorhat Road. And make sure I got that right. I say Bowman, Moorhead, and Blair. So, yep. So, problem is we got kind of 2 of those intersections to look at here. So we could take and zoom way in, and if you zoomed way in, you could see that at that point you'd have kind of a zoomed in section there, I guess you could call that. Not much to work with. If you were to zoom way out, we could take and, I guess we can go way, way out. I guess there's only 3 options there. So for doing that, you would be able to take and figure out roughly at that point, I'm thinking an inch, that's about the same distance as you have right there. So you could say that that distance between the 2 roads is going to be about 1,000 feet. Now the textbook estimated it to be about 800 feet, which is probably a little more closer than my 1,000 feet, but that's the nice part about estimating. You don't have to be exact. Example 1 is asking us how we can use the scale of the map to find the actual distance between Hagerstown and Annapolis. And what they tell us is that the distance between the 2 cities on the map is going to be 4 units. And they are using the term unit here because due to zooms on computers and whatnot, we can't exactly say that that's an inch or a foot or something like that. So they're just using that as a unit's distance. From there, we're going to take and figure out a way to measure those units between the 2 places. We're going to set up an equation involving the equivalent ratios. Ooh, we got some cool proportions going on here. And then use the scale as one of the ratios and let D represent the actual distance of the other one. So this is actually some good stuff. Proportions are wonderful things, and you're going to use them a lot in the years to come. So you can see right here that on the map, you have 1 unit is equal to, whoops, where did it go? Oh, it's bouncing back up there. 1 unit is equal to 24 miles. And then on the, we also know that on the map, the actual distance of the map is going to be 4 units, and therefore we need to use that information to find the total number of miles distance between the 2 of them. Now from here, your textbook is taking some grand leaps. They're just taking and telling you to multiply 4 and 24, and I don't really care much for that. So instead, we're going to go into that with a little bit more detail. In fact, we're not even going to do that part. We're going to cut up to there and copy that. And let's take a look at what we actually have going on here. So I'm going to zoom back out to a good number. That should work. So here is going to be the problem that they set up. 1 unit is the 24 miles, as 4 units is the D miles. And working this, we're going to do what's called finding the cross products, also known as cross multiply up, where you take 4 times 24, and that's going to end up being 96, I believe. And then on this direction, you have D times 1, which is going to be known as 1D, also known as just D. Bring them down and set them equal to each other. D is equal to 96, and that is some good quality supporting work on how to get your answers. That's using big kid algebraic math, carrying your formula or your variable all the way through. Type in our 96, we get a happy sound. Now it's your turn to try to do the same thing. I do want you to set up a proportion, solving this distance between Clarksville and Little Rock, knowing that that distance is 4 units on the map. Go ahead and do that now. How did it go for you? When I do it, I'm going to start off by setting up my proportion. The first thing I need to recognize is this right here, that 1 unit is equal to 20 miles. And from there, I can say that that is going to be equivalent to 4 units on the map compared to some unknown number of miles, which I'm going to call M. We're going to do our cross products. 20 times 4 is going to give me 80. M times 1 is going to give me 1M. Therefore, I can say that not 1M, just M is going to equal to 80. Therefore, it's going to be approximately 80 miles between the two. Skip back over to our textbook, which is right there. Let's try that again. And type in our 80 and check it, and the answer checks. Easy math. But what if you were asked to create a scale drawing of something? This is what we're going to be doing in this video. Let's see what they have to say.
Scale drawings. Designers use scale drawings when designing the layout of a room. To create a scale drawing of your bedroom, first measure its length and width, and then measure the lengths and widths of the items in your room. Make a table and fill in the measurements for the items in your room. Choose a scale for the drawing. For this project, make each 1/2 foot equal to 1 unit. Add another column to the table for the dimensions of each item in the scale drawing. Convert each measurement by using the scale. The scale for the drawing is 1/2 foot equals 1 unit, so 1 foot equals 2 units. Complete the table by filling in the new measurements. On grid paper, use a straight edge to outline the room using 1 square per unit. Choose a location for the bed. Draw the bed using 1 square per unit. Then choose a location for the dresser. Draw the dresser using 1 square per unit. This process can be used to make a scale drawing.
Well, okay then, that was really exciting. I'm intrigued on the fact that they didn't really show how they came up with their scale that they used. Maybe they were going to give us that scale on the problems. I don't know. We shall see. So let's take a look at the instruction part here to go with this. You can use a scale drawing to find the actual area of a space. First, write an equation involving the equivalent ratios to find the actual length of the width of the space, then use a formula to find the area. The drawing shows a map of restaurants drawn to scale. On the map, 1 inch represents 5 feet. And you can see that listed down here in the bottom. That's going to be our scale. What is the actual area of that kitchen going to be? The kitchen is a rectangle, so we're going to find the area of the kitchen. We first need to take and find out what the actual length and the actual width is going to be. So they set that up as a proportion. They said that 1 inch is to 5 feet, and then they said, well, we got 9 inches is going to be the length of the kitchen, so they had 9 inches is to some unknown number of feet. They did their cross products and found out that your missing length is going to be 45 feet right there. And then they did the same thing for the width of the kitchen. You can see right here the width of your kitchen. That's going to be 5 feet as well. So 1 inch is to 5 feet, as 5 feet is to 20 feet, or 25 feet. And that gave them the dimensions that they needed. Next, they said, well, it's a rectangle. And since it's a rectangle, the formula for the area of a rectangle is going to be base times height, or length times width. So they did the length of 45 feet that they found right here times the width of 25 feet they found right here to find out the total area of that kitchen is 1,125 feet squared. That is a really big kitchen. Now, example number 2 is going to be working off the same concept as that little learn page we did, where here we have a floor plan, and the scale to the floor plan is 1 inch is equal to 3 feet. So every 1 inch on the plan is going to be 3 feet in real life. And they want to know what is the actual length of the bedroom number 3, and bedroom number 3 is right there. That's a pretty big bedroom. I'm thinking that's a master bedroom, so it should be bedroom number 1, but hey. Anyhow, so we've got dimensions of 3 inches, and we have 4.5 inches here. To work through this, they took and set up their proportions. First, they said that, let's show our problem here. You had a distance on that that's going to be 4.5 inches, this one right here. So they said 1 inch is to 3 feet, as 4.5 inch is to x feet. You do need to do your cross products like I taught you, and that means that you're going to have an actual length there of 13.5 feet. From here, we need to also find out what the width of that bedroom is going to be. That's going to be step 2. Once again, the width is going to be this distance across here, which is, how do they, I guess we cropped it out, but they did actually tell us in the previous problem that that's going to be 3 inches across. So we can take and do 1/3 feet is 1 inch is 3 feet, as 3 inches is some unknown number of feet. Do your cross products again, and then you're going to find that that is going to be a 9-foot wide bedroom. So if that's the biggest bedroom in the house, is 9 foot by 13.5. That's really not a very big bedroom. 9 feet's pretty small to be in a room, and but the other ones are going to be even smaller. But hey, that's okay. From here, it's a rectangle. We're going to find the area of the rectangle by taking and saying length times width, or base times height. That means we have 13.5 times 9, that's going to give me 90, plus 27 is going to be 117, and then plus another 4.5, that's going to give me 121.5. Let's see if I did that right in my head. 121.5, and I did. Look at that. Easy math to do if you know how to multiply. Now it's going to be your turn. We're going to set this up for extra example number 2, where you've got to find the actual size of bedroom number 2. We still have a scale of 1 inch is equal to 3 feet. Bedroom number 2 is 4 inches by 3 inches. Go ahead and give me all your supporting works, and let's see if we can get the right answer. So let's take a look at how we're going to set this up. First thing we need to do is set up our proportions. So I can say that 1 inch is to 3 feet, as, I'm going to focus on that one, 4 inches is to some unknown number of feet. We'll call that x. We're going to do our cross products. 3 times 4 is going to be 12. 1 times x is going to be x, so we get x is 1x, so x is going to equal to 12, is going to be one of our dimensions. Next, we're going to use the same ratio of 1 is to 3, as this time we're going to be looking at 3 is to, we'll call that y, and from there we can take and say that 3 times 3 is 9, y times 1 is 1y, therefore y is equal to 9. That leaves us with dimensions of that bedroom, which are going to be a length of 12 and a width of 9. So area is equal to length times width. Area is equal to, a length is going to be 12, a width is going to be 9. Therefore, the area is going to be equal to 90 plus 18 is going to be 108, and that's going to be feet squared. go ahead and jump back over here, type in our 108, and check our answer. The answer checks. Easy math, guys. Real easy. For this one, we talk about an artist who uses scale drawings to create wall murals. An artist might draw a mural on a piece of grid paper, then he or she might draw such a much larger grid on the wall before painting the actual mural. You can use the scale to reproduce an actual drawing that is similar to the original but different in size, I should say. Let's take a look at how we can actually do that. We're going to do this with example 3, where the diagram represents a city park. We have 1 unit is equal to 30 meters, and we can take and reproduce a scale with a scale of 1 unit is equal to 10 meters. Now the first thing we're going to have to do to solve this is find out what the dimensions of the actual park would have been here. So you can see that this park has a length of 4 units and a width of 1.5 units. With that information, we can come down here and say that the length is going to be 4 units, the width is going to be 1.5 units. Check that. That part checks. And then we're going to say from there, all right, so 4 times 30, remember the scale we have there, that's going to give you a length of 120 meters, and 1.5 times 30, that's going to give you a width of 15 meters. So that's going to be the size of the actual park, which, by the way, that's a pretty small park as parks go. From there, we're going to move on to the next slide, where we want to take and recreate that to be the new scale drawing. That new scale drawing had a 1 unit to 10 meters ratio, and when you actually draw it out on paper, it's going to look like that. So you can see that we're really making it much bigger than the original scale drawing. To get to that new scale drawing, all we have to do is take the actual sizes that we had and divide them by the 10 for that 1 to 10 ratio. So 120 divided by 10, that gave 12, and if you count them out, you have 12 units in this width here. And then 45 divided by 10, that's going to be 4.5, and you can see here you've got 4.5 units in the width right here. From there, check our answers, and our answers check. I know that one seems a little complicated, but what you're doing is you're going from the drawing to the real thing, and then we're going from the real thing down to the new but larger drawing. And now it's going to be your turn again. We have a drawing of a baseball diamond that uses a scale that says 1 unit is going to be equal to 15 feet. And we want to choose a drawing of the baseball diamond where they reproduce it to where 1 unit is going to be equal to 30 feet. So we're doubling the size of our scale drawing here. The first thing I need to do is find out how wide my actual baseball diamond is. So I'm going to count up my units here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units across. Got a pin working here. 10 units across. It's also 10 units high, by the way. Then I'm going to set up my proportion. 1 is to 15, as 10 is the some unknown number. Do our cross products. That gives me 1D and 150. Set them equal to each other. D is equal to 150. Now we're going to take that and divide it by the 30. So 150 divided by 30 means that our new scale drawing is actually going to be smaller than the old one. It's only going to be 5 units across. Jump back over here to where our problem sheet was. Scroll down. This one here is 5 units across. That one is like 8. This one is 4. A is the only correct answer. That's what you have to do to get these problems right on your homework. Not that hard. You just got to follow the process. That's it for this lesson. Be sure to give me good quality supporting work on your homework so I can give you good quality credit. I'll look forward to entertaining any questions you have in class tomorrow.